Alrighty, I think I've got things set up on my end. If folks can let me know. Oh, whoops, I'm muted. Here we go. Okay, I muted myself. That's never a good start. Folks can let me know if they can see and hear me okay. That would be great. We got a few minutes to go till we start a conversation with Mike. But if folks in the live chat or one of the mods can just let me know if the video and audio is working for me, that would be great. Great. Thanks to J. Scott McLean letting us know we're 5 by 5. Thanks for jumping on here early, folks. We'll just chit chat here for a bit until we get the top of the hour, and then I'll do a quick announcement or two, and then we'll bring Mike in. He's in the waiting room, and he is ready to go. And sounds like everything's working okay. I'm a little nervous with the audio because when I ran the Zoom with him, he sounded a little faint on my end, but we'll see what that sounds like to you folks. And if we can just have the moderators maybe on the live chat let me know how to adjust things, that would be helpful rather than having all our good viewers there doing it at once. Yeah, so hope you're all doing well. It's fun to be here with you on this mid-August day. I'm back here at the college officially. School starts next Monday, so I've been hunkered down working on getting classes ready and going to some trainings and workshops and just all sorts of things, just kind of getting back into a totally different lifestyle and mode than what I did during the summer. But nonetheless, I've got some other things planned for you good folks moving forward, so things should look good there. Let's go ahead and do some shout outs. Let me scroll back up and see who we have here. I know I saw Janet Clancy, our good friend from the UK, is here. Kay Wick says, thanks for the hard work on these video streams. Happy to do it. These are fun for me to do. So it is work, but it's something I enjoy doing. Darren was excited for the countdown. He says, I'm good to go. Edith is here from Germany. Ake, I probably butchered that, from Sweden. Stars fans. Dan Cooper, hope you're doing well. Dan Cooper coming out of the gates hot with a question already for Mike. And that's fine. I've intentionally planned, I could ask Mike a dozen questions, but I'm probably just going to ask a few once we kind of get through our little conversation together, because I want to leave plenty of time for your questions. I think with a topic like Yellowstone, there's going to be a lot of questions. So Kay from Dorset, UK, Jean from Fairbanks, Joyce from Nova Scotia. Oops, then it bumped down again. Sue from the UK. Yeah, and I know it's late over there in Europe, so I appreciate folks jumping on. This was just the best time that worked for us over here in North America. Paul says, good evening, folks. Niles from the Netherlands. Awesome. Michael from Bethany, Oklahoma. Ed from Hampshire, UK. Denise from Amelia Island. Don't know where that is, but I should look that up. Susan, that's a good question there. You should make sure that gets through about what his role is. Ann Humphreys is here. Ma Bodie is listening to us while watching Etna erupting and checking the Reykjanes Peninsula. Wow, you're definitely multitasking and getting a lot done. So that's great. Norse Scotty Nerd from Webb Lake, Wisconsin. Ida from the Netherlands. Catherine from Sheffield. Ken from Pocatello. Thanks for jumping on with us. Jeffrey from the Netherlands. Thank you. And let's see. Aria from Idaho, eastern neighbor in Montana. Awesome. Tom. Love Vienna. Vienna is pretty awesome. Let's see. Tammy from Western Australia. Yeah, people from Vancouver. Alex from Concord, California. Robbie from the UK. We got a good, solid European crew here. I guess folks in North America, if you're working, you might still be at the office or something. Jerry from Benson, Arizona. Rebecca's at the beach in North Carolina, just making us all feel jealous. Aunt Susie from Texas, Chemo from the Finland, Bill from Olmsted Falls, Greg from New Zealand, Sherry, the wannabe geologist from California, Donna from Ellensburg, Sarah from, what is that, Delmarva, Pennsylvania and Maryland, Jenny from Wichita, Kansas, Grace from Norman, Oklahoma. If I miss you, I apologize. There's a lot of names coming in fast and furious here. Larry from Tulsa, Naki from New Zealand, Greta from the Netherlands, all sorts of good folks here. Peter from Agora Hills. Someone's moving to Iceland in 2 weeks. That's exciting. Awesome. Good, and it sounds like we're doing okay. And special thanks as we get ready to start here in a few minutes to our great moderators, Susan Helmer and Amanda Joe or Mandy Joe on the live chat. They're going to help aggregate the questions, keep us all kind of like equally yoked here as we get going. Really excited for today's guest and for the topic. I know it's a favorite topic, many people. Let's see, Larry from Castle Rock Caldera. Yeah. Roll from Myrtle Beach, Oscar from San Diego, Colleen from San Jose. Here we go. California's coming in now. We got some Colorado, Barbara from Colorado. Yes, we got some US folks now jumping on. Jeremy from Willoughby Hills, Ohio. Casper from Copenhagen, Denmark, where they use SI units, which are superior. If I have to say it, I will. Yeah, fun stuff. Great stuff. Yeah, we'll get started here in about 3 minutes. I have just a couple of announcements to go over with you. I want to make sure people know about the field trips I have planned for this fall, let you know about the next interview that we're going to have in a few weeks with another scientist, this one from Zion National Park. And I've been really enjoying doing these interviews, getting to know other people. You know, it's kind of fun for me because, you know, I carved out my path in geology, which got me to this point. I'm super happy with what I do and feel very fortunate, but it's always fun to hear how other folks pass, you know, where that took them and kind of think about like, well, that might be neat. If, you know, had I done a left turn here and a right turn there, maybe would have ended up in the same place possibly as them. So yeah, it looks like folks are jumping on and chiming in. Excellent as always. Many of you, I'm sure, are glued, or maybe not glued, but well, some of you I know are glued. Very much paying attention to the Reykjanes Peninsula in Iceland as we're, you know, sort of on pins and needles waiting for that next eruption to begin, which could be any moment now, or it could be weeks, or possibly even a month or more away. We'll just have to wait and see as things go forward. So yeah, we'll get started here in just a minute. Thank you all for jumping on early. If you're waiting for this thing to begin and you're feeling a little impatient, we usually just kind of do a little informal chat here as people are jumping on. The live chat, it's fun for me to see where people are chiming in from. And then once we hit the top of the hour, I will start this thing officially. In fact, let me go ahead and I should have done this already. Switch over to, let's see here, what am I going to switch over to? Well, I wanted to pull up the, maybe it's down right now. Yeah, let's pull up some of my announcements and things, my little kind of getting us started little logo thing, and then we'll get started here. Oops, I think I had that there. Switch that over. And now we should be doing okay. Actually, I'll just leave it like this. And then I need to add that in there. So, okay. Sorry, friends, just trying to get a couple other things situated here. Let's see. Okay, there we go. All right, great. It is now 3:01, so I apologize for starting a bit late, but thank you for joining me. I'm Geology Professor Shawn Willsey. It is 3 o'clock here, Mountain Daylight Time. Greetings from wherever you're joining us from and whatever time of day it is, or night, wherever you are. We are doing a special live stream broadcast here. We're going to be speaking, most of our time we'll be speaking with Dr. Mike Poland of the USGS, and he works and heads up the Yellowstone Volcano Observatory. And quick little bit of background, I met Mike briefly, gosh, I don't even know, it was maybe 12-ish years ago when I took a group of students to Hawaii and we wanted a tour of the HVO, the Hawaii Volcano Observatory that the USGS runs there. Mike was gracious enough to walk our students around, show us kind of what they do, talk to us for, I don't know, 40 minutes, an hour or so. And he's gone on to do great things since then, and I'm excited to get to talk to him here in a second. But just quick announcements. So just a couple of things here. I did do a video recently where I talked about some of these field trips I have coming up, so I just want to make people aware of these. So I have a slate of field trips in northern Utah in late September, another set of field trips here in southern Idaho in mid-October, and then other locations closer to Twin Falls here in early November. So you can go to my website, willseygeology.com, and you can get all the information there. It's all automated and set up thanks to Amanda Joe. So quick announcement on that. If you want to fly into Salt Lake City, that would make coming to these 3 field trips pretty easily. So I know many of you are not anywhere close to this region, but I am trying to spread out a bit slowly as this kind of grows and get to more areas and put together more field trips for people, because I think that's almost maybe the most rewarding experience we can have together is outside looking at the rocks themselves. And then just a quick reminder, not sure if this is going to be a live stream or recorded. I need to see what her preference is, but we'll be speaking soon around the end of the month with Robin Hendrick, who is a physical scientist at Zion National Park. She gets to do all sorts of different things, and real excited to see what types of science she's involved with there in Zion National Park. So just a couple quick announcements there, and we will now, without further ado, with those announcements in mind, if I can figure out where all my tabs are here, switch over to where's it at? Switch over to our discussion with Mike Poland. Sorry, I'm trying to figure out how to get back to where I was before. Let's see. All right, sorry team. Something's a little different here. They changed something on our computers here at the college, and things are everything looks a little different, and so having a little bit more trouble getting things going here. All right, how do I get, return to the meeting. Oh, there we go. Okay, wow, that was more painful than it needed to be, for sure. Okay, so sorry about that. We will now get Mike into, there's 2 of me. Let's get rid of that. There we go. And we'll bring Mike in here. Sorry about the rough start. So we go here, and okay, so he should be jumping in here any second. There he is. Awesome. Oh, now I can't hear him at all. Hold on. All right, go ahead, Mike. Sorry.
No problem. How's that?
I can't hear you at all, Mike. Hold on.
Testing 1, 2.
Okay, I can hear you faintly. Let's see how it sounds for folks there. We're going to wait here with the lag.
Okay, I'll just say a few words to make sure that it maybe comes across, hopefully.
Yeah, just tell us about your breakfast or something this morning.
Well, I had some good coffee.
Oh, did you make your own, or did you purchase it, or?
Made our own from Deschutes, from Sisters in Central Oregon, a good volcanic region.
Yeah, good soils there. So
good coffee comes from good volcanoes.
Okay. So it sounds like I'm sounding good, or you're sounding good, but I'm echoey. I think I just might have fixed that a little bit. So is that better? Manda Joe, if you can let me know if that sounds a little bit better. Sorry, Mike, we'll get this dialed here in like the next few seconds.
No worries. It's amazing we can do this at all.
Yeah, it is. Yeah, the technology's great. So I'm going to maybe turn mine down just a skosh too. Okay, how's that sound now, team, on my end, since I was the problem with this part of it? Mike sounds great, so that's perfect.
Okay.
Any better on mine? Still echoey, a bit of an echo on my end. Is it okay? Is it awful? Let's see.
I wonder if it's getting picked up by my mic or something like that.
We need an audio engineer is what we need. So, okay. Yeah. I've got my headset down, and I think we should be okay now. So, yeah, it says it's still echoey. Some people are saying it's awful. Shoot. Let me see here. Yeah, not sure what the deal is on my end. Yeah, most people say it sounds okay. Let me try one more thing here. And since you'll be talking mostly, maybe it's not so bad. So, someone also, if you have me on speaker on your end, but I don't think it's anything on your end. I think it's more my end. So,
I'll go ahead and mute my microphone when I'm not talking, just in case.
Okay. Yeah, I think it's okay. Let's just go ahead and start then. So, sorry about the rough start there, Mike. Yeah, well, first of all, welcome. Thanks for joining us today. We've got a lot of people here that are anxious to get to know you a little bit better, find out what you do, learn more about Yellowstone and the Volcano Observatory. Let's just kind of start at the beginning, like your background, where you grew up, kind of how you tasted the geology Kool-Aid back in the day, and kind of how that went.
Well, I grew up in Sacramento, California, not too far from Lassen, and really got into volcanoes, I think, because of Mount St. Helens in 1980. I was a kid, and I remember it very distinctly, sort of being glued to the TV and following all of the reports that were coming out of Mount St. Helens, both in the build-up to and then the big eruption on May 18th. And then it was just sort of what we talked about in school after that. There were units on volcanoes and things like that. I remember in second grade, having the volcano pack, the Cascades, and one of them we had to find like a maze out of the magma chamber up to the top at Mount St. Helens. Another one we had to do a connect the dots for Mount Mazama, which was kind of silly, right? Because it was just Crater Lake up. So that just really got me into it. And then knowing that Lassen was right there, my dad took me camping up at Lassen and Shasta. I just got the bug. I just was, I couldn't say no to volcanoes at that point.
So you knew at an early age then that you were going to go down that road somehow.
I knew I was interested in it, but as I got closer and closer to thinking about careers and stuff, I remember saying, I really don't see myself as a geologist, because it seems like all they do is sit around in deserts with a paintbrush dusting off rocks. And it wasn't until I got to college and started meeting geology professors and started taking classes and realizing, this is pretty neat, and the people are great. So that really spurred me into it. And once I sort of got into it, I was like, well, if I'm going to do something, it's got to be volcanoes. It's always had to be volcanoes. So that that tore it for me.
So, what college were you at? Like, which school were you going to, and kind of maybe walk us through that just a little bit?
I went to University of California at Davis, so I didn't stray too far from home. It was far enough to, get away from home, but not so far that I couldn't go home on weekends and do laundry. And then for graduate school, I went to Arizona State down in Tempe. So that's sort of the career path. And after that, I was lucky enough to launch myself right into the Cascades Volcano Observatory right after I finished. So I had a nice, and I'd say somewhat lucky progression. I was sort of in the right place at the right time when jobs were available.
Right. And so your degree is in, your graduate degree is in geophysics, correct? Maybe explain to people who, well, go ahead and answer that question first, and maybe make sure that I'm on the right path with that.
Well, ASU at the time didn't have different separations, and so I think my degree there is technically in geological sciences.
Okay.
But yeah, we didn't have a specific track for geology, geophysics, volcanology even. But the reason I went to Arizona State was that it was known as a place for volcanology, and so that was the focus. That was the reason I went there. It was the emphasis there, and then the people that I wanted to work with.
Right. And so explain to people, a lot of times I get questions about all these sub-disciplines in geology and what they are. Like, maybe explain in your own words, like geophysics and what that involves, what kind of aspect of geology that is.
I think of geophysics as being trying to understand things that we can't see directly. So using earthquakes or magnetics or electrical resistivity or ground deformation, things like that to sort of probe what's happening beneath us. Geology is about being able to see things, looking at fossils, looking at stratigraphy, the rock layers, trying to get dates out of those rock layers, trying to understand exactly how a sequence formed. And geophysics is more about, all right, well, we know that there's a source of earthquakes, say on a fault, but we can't see that because we can't get down there. We can't, dust off the outcrop. So how can we use measurements that we take at the surface to better understand what's happening beneath our feet? And so it's a bit of an inference. We're trying to, maybe it's a bit like being a radiologist, using x-rays to try to see within the human body, or an MRI or something like that. We're using different methods like that to try to see what's going on in places that we can't directly observe.
Right. So you're using, it's just like a radiologist. You're using indirect data, like you're not going there, but you're using other forms of data to get knowledge about, in this case, the subsurface or whatever. So
I think that's a good way of putting it. We're using an indirect way of seeing what's happening beneath the surface, in the same way that, the MRI expert kind of can say whether or not your knee is injured based on that data that they're getting, which is not a direct measurement.
Right. And you knew early on, even though you went with the geophysics angle, or sort of as a sub-discipline, but you knew you were going to use that to study volcanoes specifically, because geophysics, as you well know, has lots of applications. It's a tool we use. Like, it's used in oil and gas. It's used in every aspect of geology I can think of. If you can get geophysical data, that's going to help you solve whatever problem or issue you're trying to work on.
Yeah, I was lucky in that when I was at Davis, I had a professor that was an expert in active tectonics, basically, current motion of tectonic plates, earthquake faults, volcanic activity, landslides, things like that. And he had a project going on in Hawaii and invited me to sort of go as his field assistant. And I went early and worked with a group from Stanford University that were setting out GPS stations around Kilauea volcano. And they were doing that so they could measure how the ground was moving. And I was floored by the idea that we could, using these antennas that we set up, over a benchmark at the surface, over a little brass disc or something that we can use as a kind of a stable point, we could measure millimeter scale motions with this technology. I just couldn't believe that was even possible. And so that's really was my entry into wanting to do geophysical measurements. And physics to me has always made sense. You push on something, it moves, and friction or drag will slow it down. There's a logic to that I find appealing. Chemistry has always been, that to me is magic. You combine two things and get something else that's totally different. I can't wrap my head around that. So that was why I was always attracted to the physics part rather than, say, chemistry.
And I remember my physics class, like, as long as it was like tangible, like, you know, like you shoot off a rocket at a 40-degree angle with this velocity, I was fine. But once it got abstract, like when we got to magnetism and some of those things that felt more abstract to me, it's like, ooh, this is tricky. But it seems like you came into, I mean, you really did time it well, because you came into a world where geophysics and technology were doing really big things. You know, had you come into it 30 years earlier, it probably would have felt still on the cutting edge at that time. But like the tools that are used, you know, over the last 20, 30 years with volcanoes and other applications is like really pretty amazing when you look at what we're able to do.
Yeah, there's been quite an evolution in volcano monitoring. You know, my specialty is in ground deformation, you know, how the ground moves around volcanoes especially. And, you know, I would say 30 years ago, except now it's probably more like 50 years ago. The main way of measuring how the ground moves was, say, to use lasers. And you would shoot a laser from one point to another, and that laser would then bounce back. And you'd measure the travel time it took and then divide by 2, and you could get the distance between those 2 points.
Right.
And then you do it again, and you'd see whether or not the points had moved, whether one was farther away from the other, and then you could tell whether the ground was inflating or deflating, or, you know, what was happening. And that was incredible for the time. That's how some of the first real measurements of a lot of different kinds of volcano and earthquake motion were made. And now we're doing it with satellites, with GPS, with radar satellites that are, you know, beaming radar pulses down to the ground, measuring the return, and we get these basically photographs of how the ground is moving. So it's difficult to fathom the advances that have occurred in the last few decades. How space-based stuff has really made a lot of what we do possible.
Right. Yeah, it makes you wonder, like, you know, 20 years, or, you know, when you're getting ready to retire, like, where will it be then? Like, no one can even like really predict, I don't think, like where it'll be.
Yeah, I get that question. So, like, what do you think the next great advance is going to be? And I think, man, I have no idea. It's going to be something that I probably can't even imagine. And I think, you know, 30, 40 years ago, whether or not people could have possibly imagined, you know, measuring deformation from space using radar waves. I mean, maybe that was imagined, but to be able to do it so regularly now, yeah, 20, 30 years from now, I couldn't even begin to guess what we're going to be doing next.
Yeah, now we're like bummed out when, oh, we can't get the latest INSAR image till like next Thursday. Like, oh, what a bummer, right? Like, we're just so spoiled. So yeah. So you started out after grad school. I mean, I met you in Hawaii. Was that like, you said you went to the Cascade Volcano Observatory first? Sounds like you've been in the USGS right out of school the whole time. Maybe walk us through just a few things you learned at each station, I suppose, along the way coming to Yellowstone.
Sure. So yeah, I started out at the Cascades Observatory, and I had three plus years there. And my job was to bring INSAR, so this is, you know, satellite measurements using radar of ground deformation, bring that into sort of a tool that the Cascades Volcano Observatory could use. And I'd say that I met tremendous people while I was there. It was very formative for me, but what was perhaps the most spectacular experience was being involved in the response to the eruption of Mount St. Helens that started in 2004. So that was late September of 2004. Suddenly seismicity really started ramping up, and we didn't have much of a monitoring network, a permanent continuous monitoring network at St. Helens at that time. There were some seismometers, but there was only one GPS station. So this was really about the time that continuous GPS was starting to become mainstream. And so I was involved in an effort to get a lot of sensors installed around Mount St. Helens. We were doing that as quickly as we could while the unrest was ramping up. I was involved in the effort to put a camera out to catch whether or not there was anything happening in the crater, and that ended up being a tremendous the video we got of the lava that came out of the crater from that camera was exceptional.
Yeah.
I was really amazed at how useful that was. And of course, now there's cameras everywhere. So that was really formative for me because I learned a lot about the technology, and I also learned how to respond to a crisis, how to communicate, how to work with other volcanologists, how to really be part of a team. And so that was incredibly formative. And I used all those experiences when I went to Hawaii in 2005. I was at HVO, the Hawaiian Observatory, for 10 years. And I participated in all kinds of responses there and all kinds of research. Hawaii was an incredible natural laboratory for volcanology. You literally walked out the office, walked right outside.
Yeah.
And 10 minutes after you leave the office, you were on the rim of one of the largest lava lakes in the world. So Hawaii, I think it kind of came to you. The ground was always moving around. It was dynamic. It was always changing. That was something that I found really exciting. It was tough too, because I was involved in some responses there where I was talking to people and had to say, if this lava continues moving, your house is in danger.
Yeah, so it gave you more of the human side. Yeah.
And that was it was difficult to have those sorts of conversations, but I'd never felt that my job mattered as much as it did in those times. A lot of times you can sort of get ivory tower, like, oh, yeah, I'm doing this interesting research on gravity variations at volcanoes, and it's all really, all very academic, but it got real during those crises. And it was difficult, but it gave me a real appreciation for the importance of communication and talking to people in a real straightforward way. And then I came back to CVO in 2015, and I began working in the Cascades again, but then had the opportunity to work in Yellowstone starting in 2017, and I'm not going to say no to that. So I've been pretty lucky to have the experiences I have.
Did you notice a difference because Hawaii, there's always, it's a different system volcanically, and it's one in which things happen with much more frequency. So I would guess it's more exciting in a way than monitoring the Cascades, which, when they are active, it can be dramatic, but largely day in and day out, it's very small increments of activity. Was there kind of more of a rush in Hawaii, and you enjoyed that more or less, or maybe it was too busy? I don't know.
In Hawaii, I enjoyed the idea that every day I woke up and looked at tilt data or GPS data or whatever, I might see something new. There might be a DI event. That's where the whole volcano would deflate and then inflate. It sort of did that all the time, almost like it was breathing. Maybe there'd be an intrusion of magma that was moving down one place or another, or a backup of a lava tube system, which was causing an area to inflate. It was always changing, and that was exciting and interesting, and it kept you on your toes. For the Cascades, I think there is personally, I guess in my case, and I don't think this is true of everybody I work with, but I think there's a danger of getting complacent or like, well, things don't change that fast in the Cascades, and they don't. Cascades volcanoes will seem to go for a long time with not a whole lot of changes, and then like Mount St. Helens in 2004, you might ramp into something in a relatively short time frame. And I think that's especially true at Mount St. Helens because that system is very well oiled. It's an extremely active volcano.
Right.
So the key in the Cascades is to be ready and to be watching things and to have plans in place. And I think in Hawaii, they're exercised quite a bit. And so there's sort of a natural tendency to be able to respond quickly and efficiently. And bringing that experience to the Cascades and working with the people I do, I think the challenge I have is to make sure, you have to stay vigilant and ready because, even though I've, woken up every day for the last 9 years and not seen huge changes,
right, that
doesn't mean that tomorrow there won't be some big changes at, say, Mount St. Helens.
Yeah. And now you're at a volcano that has even larger, recurrence intervals between eruptions. If you worked your whole career at the Cascade Volcano Observatory, there's a good chance that one time during that 30-year career, you're going to see an eruption of some size. I would think that's a pretty high probability. And now you're at a volcano where it's less likely, but then it's punctuated by something like what happened at the Biscuit Basin just a couple weeks ago.
Yellowstone is, I'm not worried about the volcanic eruption at Yellowstone. We know from seismic imaging that the magma chamber is mostly solid. There's just not a whole lot of magmatic system activity. What I've always been concerned about, and I think geologists in general have been concerned about at Yellowstone, are two things that are likely on human timescales. One is a strong earthquake, magnitude 6, magnitude 7. And there are all kinds of faults in that region. There was a magnitude 7.3 in 1959. That's still the largest earthquake ever recorded in the Intermountain West. And it caused a lot of damage. Landslide dammed a lake. It killed 28 people when the landslide went through a campground. Those are devastating events. Nothing to do with the volcano, but that kind of thing is going to happen again in the future in that region and elsewhere in the West. And then hydrothermal explosions, again, not involving like a direct connection or direct contact between magma and water. It's not a volcanic event. It's sort of a steam-driven event caused by pressure changes in the very upper surface or shallow levels beneath the surface. And so those are the things that are likely to happen in Yellowstone. And yeah, the Biscuit Basin event really highlighted that. I think the hydrothermal explosion hazard was sort of underappreciated because there hadn't been anything really dramatic like that that had been caught on video. And then, July 23rd, we had that.
Right. Yeah. So yeah, it definitely got people more aware of the hazard, even though USGS has put out, information and flyers for several years that I've seen that point to them being as common as we now know they are. But you're right, it's in the wintertime, it's in the backcountry, it's at night. There's a number of factors why we hadn't really seen one. And then this one was caught in the middle of the day with visitors there in the summertime with cameras, and so it became a much bigger event. So, yeah.
Yeah, I've had a few people ask me, if these are relatively common events, then how come no one's ever recorded one before? Well, one reason is that it's only the last decade or so we all have, video cameras in our pockets.
Right.
And another is, Yellowstone is a huge place. There's a lot of thermal areas in the backcountry. Things happen at night. Things happen in the winter when areas are not nearly as accessible. And so an event like the one that happened at Biscuit Basin, that might be kind of a one to few decades sort of recurrence in terms of size. But small ones happen all the time. Yeah. There was one that we recorded with geophysical measurements on April 15th in the Norris Geyser Basin. And the only reason we know about it is because of a big seismic signal and a big infrasound signal, sort of an acoustic signal. So we caught the explosion, but there was no one there at the time. No one saw it. So the only reason that we have some data about when it occurred was based on the geophysical monitoring.
Right. Yeah. So they've gone unnoticed, and now we're starting to figure out the signals where we can see them. Well, maybe tell us more about, now that we're kind of caught up to where you're at with your current position, tell us a little bit about the Yellowstone Volcano Observatory, how it's a little different maybe than some of the other ones in the USGS system, and then kind of what your role is there and what your job's like.
When I think of Volcano Observatory, I naturally think of something like the Hawaiian Volcano Observatory, especially the building that existed prior to 2018. It was right on the, you were there, right? It was right on the rim. It has an observation tower. It was observing the volcano. Even the Cascades Observatory, we have a view of Mount St. Helens, all the telemetry tower right outside the observatory. So I think of an observatory as being a facility, often with a view of one or more volcanoes. Really, HVO is classic in that regard. But Yellowstone does not have a building. We are not a facility. It is and always has been a virtual observatory. And it is also not just the USGS. It is a consortium of 9 different institutions. So YVO is USGS, Yellowstone National Park, a group called EarthScope. They monitor ground deformation all over the western United States, and in fact, well beyond that. Then there's the University of Utah. They do all the seismic monitoring. University of Wyoming, Montana State University, just right there in Bozeman. And then the state geological surveys of Idaho, Montana, and Wyoming. So we all work together to try to better understand how Yellowstone works, to put out information about new scientific findings, about hazards. And my job is to coordinate all of that. So I have the main job for hazards messaging, and then also making sure that we're really well focused and working together to better understand how Yellowstone operates. So that's sort of the job, and it's a good one. I get to work with a tremendous team and a lot of great people, and it's been a tremendous learning experience too. So I've had a really good experience with YVO.
Right, that's incredible. And as you're talking about that, I'm thinking about how challenging it would be. I mean, it's challenging enough to be in charge of a staff within an organization, but you're sort of the head person over this organization that is composed of 9 entities with who knows how many staff that are onto that. So like, this doesn't have to be like a logistical management seminar or anything, but is that a challenge, or is it easier than you think otherwise, or everyone's kind of got their lane and their role?
Yeah, I think the roles are pretty well established. Like Utah does a lot of seismic work, but there are seismologists at the Montana Bureau of Mines and Geology that also contribute, and they collaborate very well with the people from the University of Utah. So it's I think it may be like a family, and a family that gets along really well. Maybe it's not a great example. Family isn't a good example.
Right.
But we know our roles. We have our levels of expertise, and we all contribute to better understanding Yellowstone. It's a really complementary set of scientists that are engaged there, doing all manner of things, from trying to determine the ages of eruptions and trying to determine the composition of the ground beneath us, and trying to understand better geyser activity. It's a sort of like Hawaii, taking advantage of the fact that Yellowstone is an amazing natural laboratory. It also has these hazards, and so we're also trying to better map out the hazards and understand their mechanisms. But it works well, I think, because the people that are behind the scenes doing all the work are fantastic people that want to advance knowledge about this amazing system.
Right. So you've been there since 2017, you said, right? So for 7 years. Maybe, I don't know, I have so many Yellowstone questions. Like two or three things that you wish the public knew about Yellowstone, like the message you can't seem to get out most, strongly enough. Like, I have to reiterate this and this and this.
Well, up until 3-ish weeks ago, it would have been that the real hazards on human timescales in Yellowstone are things like hydrothermal explosions. I've often said that this is an underappreciated hazard. I think the hype around Yellowstone is the gigantic caldera-forming eruption. We're not really worried about that. Geologists in general are not worried about that for various reasons. The magma chamber is mostly solid. There isn't really a lot of unrest that signifies there's a lot of rejuvenation of that system. And so this hydrothermal explosion has always been the most likely thing to happen in Yellowstone and pose a hazard to people, especially if there were, an event that happened during the summer in a popular geyser basin during the day. And that's exactly what happened on July 23rd.
Right.
So I'm not so sure that's underappreciated anymore. I think it maybe that appreciation grew a little bit thanks to that event. And unfortunately, no one was hurt. So hopefully it did a good job of raising awareness without causing any injury. But that would have been the main message I tried to get at. And I kind of feel like, wow, that message might be out there now.
Yeah.
Another thing, I guess, is there's a lot of misconceptions about how Yellowstone works volcanically. And one of the most common misconceptions, I think, is that Yellowstone is overdue.
Yeah.
I hear that one all the time. I even did some polls and some talks I gave, like, which of these misconceptions have you heard mostly? And the overdue one was the most common. And I don't know where that came from.
Well, it's bad math. That's where it came from. It's three events, and you just calculate the recurrence interval between those three events, and then that's where I think it came from. But.
Well, somewhere along the line, somebody started saying every 600,000 years. And it's been 631,000 years. Therefore, we are 31,000 years overdue. Like, well, if you do that math between the three most recent eruptions, you get a recurrence interval of like 725,000 years. So that math doesn't even work. And really, why would you base that on three numbers?
Yeah.
Right?
Poor statistics.
Yeah, it's bad statistics, and whoever came up with the 600,000 made it up, and somehow that took hold. So I've learned a lot of lessons about communicating as part of this job. And one of the lessons I learned is that it seems like the first thing that's heard is the one that's most remembered. So somewhere along the line, somebody somewhere said 600,000, and that's stuck really hard, and it's been hard to dislodge.
Yeah, that's crazy. Yeah. I think we all kind of fight that a little bit too. Well, maybe what's like the one thing, the most significant or impactful thing you've learned about Yellowstone since arriving 7 years ago? Like something, you're knowledgeable, geophysics, you've worked at all these other volcano observatories. And now with 7 years under your belt, what's the one thing you can look back at and say, wow, I didn't know that or didn't appreciate that as much?
It probably had to do with the geysers and the hot springs and their chemistry. I mentioned before, right? Chemistry is not my thing. That's not where I go.
Yeah.
And when I first started this job, I had people coming up to me talking about the acid sulfate systems and the neutral chloride systems and blah blah. And it took me a while to really understand, the process of phase separation that gives you this chemistry or that, that was all really Greek to me. And it took a while to understand the mechanics that were happening in these systems, which are dominated by both physics and chemistry. How water boils due to changes in pressure in the shallow subsurface, and how the chemistry is affected by the interaction of water, magmatic gases, the very ground itself. So diving into that has been illuminating. I don't pretend to understand it near as well as some of my very wise colleagues that study hydrothermal systems, but that's been really interesting to be able to go to a hydrothermal system, a thermal area in Yellowstone, look at the landscape, understand what's happening beneath the surface, and that ties to hazards too.
Right.
So places where we might see explosions like we did on July 23rd tend to be the systems that are dominated by boiling water and not by steam. There are a lot of steam-driven systems at Yellowstone, and the steam's already there. Whereas you go to a place with a lot of boiling water, there's liquid water that can convert to steam, and that's where you can get the really big explosions, these big hydrothermal events. So I think that's been the biggest lesson for me, is putting all that chemistry together, because it's been something that I've traditionally been
it was a blind spot for you, and now you've kind of learned a little bit. So
yeah, and it's been really interesting, to be honest. I mean, I really am not a fan of chemistry, but this has been a fun experience, sort of learning how these systems work in the chemistry, and this goes down to looking at how various weird chemical species get dispersed, like arsenic and mercury and stuff like that. It's just been fascinating.
Yeah, no, it's so interesting and so dynamic in so many different ways, and you can, the chemistry, the geophysics, the earthquakes, the volcanic systems. And then ultimately it's all connected somehow. So that's, then you got to have the big picture, you got to have the close view of the details and what the processes are, but then the big picture view as well.
Yeah, that's one thing about volcanology that I love, and about the Volcano Observatory system, is that I think we are all trying to tell a story, right? We're trying to use the data set that we care about most to tell the story of what's happening beneath our feet, or what the geologic history of a place is. And in an observatory, or working with an active volcano, my story, based on, say, ground deformation, might be somewhat different from the seismologist story, or from the hydrothermal expert story, the geochemist story. And the fun and the challenge in volcanology is having all of us get together and tell our stories to each other, and come up with a way to make one story that fits all of our data sets. Because, my story is not necessarily going to fit that which would satisfy the data that the seismologist gets. But somewhere we can find some common ground. Mm-hmm. We can find a story that fits all of the observations. And that's when I think real neat advances can be made. And that's the fun of being in an observatory, because you're surrounded by colleagues that have expertise that's different from yours. They tell different stories, but it all roots in the same fundamental process, and that's what we're trying to figure out.
Yeah, like the common theme is the place. You guys are studying the same location, but with different techniques, different angles, different focus. Yeah. Well, maybe one more question, and then we'll switch over to the viewers here. I guess the last question I have for you is, as we both know, and as everyone I think knows, Yellowstone is a topic that's rife with everything, just this called misinformation, I guess is the way I would put it. And so I'm interested in knowing, as someone who teaches and tries to fight that misinformation, what are some techniques, or how do you do that as the scientist in charge at the YVO, like when it comes to some of the hype and the things that swirl around Yellowstone?
Yeah, it's pretty frustrating. I kind of feel like we've got to be in a lot of different places providing information. And so I feel it's important that we're a source of detail, source of new findings. So, for example, if we discover a new thermal area, we ought to be telling the world about it. And we have, for the most part. But sometimes it might be in a scientific publication, or some of these areas that aren't quite as public. So I've been really happy about finding ways to communicate some of these really cool findings just with everyone. We do that through weekly articles that we put online. We started doing videos. We've got annual reports that talk about all the different activity that might have happened in Yellowstone over the course of a year. So, I feel people like to get information in different ways. Yeah. So I feel like we should serve that. And by doing so, we provide kind of, I hesitate to call it an alternative to the clickbait misinformation, but I feel like there are always going to be holes in the information landscape.
Right.
And to the extent we can fill those holes, it means that it provides less fertile ground for misinformation to sort of grow.
Yeah, and I think you've been at the USGS long enough to see there's an appetite from the public to understand science, to learn more, to know more. I think we all probably naively thought years ago, oh, the public doesn't want to look at seismic data and whatever. This is kind of nerd land. But there's a big appetite for it, and I think the USGS and a lot of other entities too have done a really good job about kind of closing that gap. Because as scientists, we've traditionally been not good at communicating well with the public in terms of scientific information. And I want to just give you a quick kudos to you. I think you're a very clear communicator. The little things in the videos I've seen you do, they're to the point. I think they're effective, and it would be I think it's great that you've kind of pursued that avenue. Because I sense that you maybe feel obligated to do it, but I feel like you want to do it. Like you actually have a passion and a desire there.
Well, thank you. I appreciate that. Yeah, I do have a passion. I mean, I enjoy talking to people about volcanoes and Yellowstone, and it's endlessly interesting. And it's the things that frustrate me. It's not just the obvious misinformation that's online, but it's also like documentaries that have to focus on the fact that Yellowstone a long time ago had a huge eruption and at some unknown point in the future might or might not have. And frankly, that kind of stuff strikes me as lazy. Go to Yellowstone, look at it. The place is incredible. Right. It is amazing. And I just think it's lazy to have to appeal to some unlikely, not going to happen in our lifetimes thing to get people to watch your documentary.
Yeah.
When, it's got 50% of the geysers in the world are in Yellowstone.
Yeah.
Where boiling water shoots out of the ground with some regularity. The microbial life there is incredible.
Yeah.
It's
like it's not enough, right? Like it's not enough, so we got to sensationalize or make it even more so. When at face value, it's plenty amazing enough. But yeah, that's sort of
that's exactly the way I feel. You don't need to make it any more spectacular than it already is. It is incredible, and so I think any places that sort of go to it just feels like lazy news making.
Yeah, that's the world we live in. So. Well, are you ready for some viewer questions? You still got a lot of energy left? Okay.
Absolutely.
Okay, so from Dan Cooper, he says, is seismic tomography or GPR utilized or useful in mapping the plumbing systems in Yellowstone with the geothermal features?
So yes, not so much GPR. There has been some GPR done, but it just doesn't see that deep.
And GPR, real quick, is ground penetrating radar. Yeah.
Yeah. So the ground penetrating radar just doesn't do very well, but seismic tomography does do well. And that's been a relatively recent development, say the last decade, especially because there are now these little coffee can sized seismometers that run on batteries for about a month. And so you can go out and deploy a whole bunch of them in a focused area, let them run for a month, and then pick them up and download the data. So you've got this mini seismic network that you can just throw out there. That's been done around several of the geysers in Yellowstone, Old Faithful, Steamboat Geyser, many others. And it allows us to see beneath the geyser. And there are some amazing examples of Old Faithful, for example, looking at the seismic noise, and you can see it rising up and then sitting in the bubble trap, which is about 100 feet beneath the margin of Old Faithful. And then an eruption happens, and then the seismic noise goes way deep again and rises up again. You can basically see boiling water moving around in the subsurface.
Right. And so you can sort of get a graphical representation of the plumbing system then that feeds, because you can see those zones.
Yeah, absolutely. And that one of the really neat results came from Steamboat Geyser, tallest geyser in the world. It shoots water up 300-400 feet. And the thought was, all right, we're going to look at the plumbing system, because there's about 300 feet away, there's a place called Cistern Spring. And when Steamboat erupts, Cistern will then drain, like somebody will plug that. So they got to be connected. Well, the scientists from the University of Utah put this nodal seismic network out, and they were not able to see the connection between the two. They went straight down several hundred feet. They never saw where the two connected. So that's sort of an interesting result in itself. The plumbing is independent, at least for a few hundred feet. So yeah, the seismic tomography has been outstanding at investigating some of these geyser systems.
Cool. Okay, from Sarah Elizabeth, how deep are the fumaroles in Yellowstone and how many are there?
Oh, goodness. There are a lot. We sort of throw out casually, well, there's 10,000 thermal features in Yellowstone. That's probably an underestimate, or it depends on how you count them.
Yeah.
How many of those are fumaroles? Well, I couldn't say off the top of my head, but maybe somewhere in the neighborhood of a quarter or something like that. You tend to see the fumaroles at these acidic systems that are steam dominated. And so go to a place like Mud Volcano Thermal Area. That's where you'd find a lot of fumaroles. There's a few in the Norris Geyser Basin area. And so those, none of these hydrothermal systems go particularly deep. It's not like things are going all the way down to the magma chamber and then circulating back up, because the rock gets too hot and you sort of circulate back up before you get to that point. But they're really common features that you see in geothermal systems in general. And the kind of gases that come out are indicative of these kind of geothermal systems where there's a lot of water and some cooling magma body that's several miles.
It's more a chemistry thing that controls where the fumaroles are. I always thought it might be water table related, like a deeper water table might give you a fumarole, whereas you have something at or close to the surface that would give you a spring or a geyser. I don't know.
Yeah, that can play a role. So sometimes you see in the lower elevations, that's where the water comes, and then the gas can separate off from the water and make it up to higher elevations. And so at some point times you'll see, like at the bases of some of these big lava flows that occupy Yellowstone, you'll have a lot of these watery features that are kind of neutral in composition, but then the acidic gases come off of that, and they can feed fumaroles and mud volcanoes and things like that a little higher up, and they have an acidic composition.
Okay. All right. Yeah, I want to talk about more on each one of these, but I want to make sure we get to all the questions. From Eric Clayton, I've seen two paths put forward for the main magma conduit to Yellowstone, one trending southeast from the Butte area and another trending northeast from the Sonora region of Mexico and Arizona.
Okay, so I think what that's referring to is the trail of the hotspot and then the plume that is feeding the hotspot. So the volcanism at Yellowstone, the heat, is fueled by, we think, and I think most geologists think this, but not all of them, a plume of hot material that's originating deep within the Earth, and it rises up towards the Earth, and as it gets close to the surface, within many tens of miles, it starts to melt. And that will then feed heat and magma up towards the surface, and you'll get eruptions. That plume seems to originate from near the core mantle boundary, so way deep within the Earth. And it looks like the root of that, based on some of the seismic imaging that looks at sort of the whole Earth, is somewhere down, like beneath Baja California, somewhere around.
Right, but it's so deep, and it's coming up mostly vertically, but at a slight deviation of an angle, so it ends up far away just in terms of horizontal distance. Yeah.
Right. Now, superimposed on that system is the surface of the Earth, which is made of these, tectonic plates that are moving around relative to one another. So the plume is relatively fixed, and the plate is moving over the top of that plume. And so you'll get sort of a volcano, and then the plate will move, and you'll get another volcanic system, the plate will move, and another volcanic system. And so if you look at a map of Yellowstone and then looking west through Idaho, you'll see the Snake River Plain is this sort of swath of low topography. And that swath of low topography is a bunch of lava flows, and beneath the lava flows, a bunch of material that looks just like what has erupted at Yellowstone. So there's basically a path of ancient Yellowstones that goes all the way to the Oregon, Nevada, Idaho border. And so that's the surface expression of where the plume used to be, but plate motion has moved it away.
Yeah.
So you're seeing kind of the trail of volcanoes, and they get older the farther you get from Yellowstone. The old caldera systems are at that Oregon, Nevada, Idaho border region, then they get younger as you march across the Snake River Plain to where Yellowstone is today.
Right. Yeah, fascinating. All right, from Larry Mosley, I was recently at Yellowstone and was viewing the rock layers at Little Grand Canyon. I'm interested to know more about the columnar basalt layers that are visible in the park and in the region?
So those columnar basalt layers erupted between 2 and 1.3 million years ago. And they were part of great big eruptions of basalt, which is sort of a low silica composition, kind of what comes out of Hawaii. And those kinds of eruptions were occurring at that time and then laying down these sheets of lava. And as the lava flows slowly cool to the interior, you get these columns that form that look a lot like Devil's Tower or Devil's Post Pile. If you've ever driven through the Columbia River Gorge in border of Oregon and Washington, you'll see a lot of those features. Giant's Causeway in Ireland. I mean, they're all over the place. And it's just a sign of slow cooling. And it gives you those columns. So those things that you see in the downstream part from the Grand Canyon, that's near Calcite Springs Overlook and
Tower Junction.
Yeah, those are those lava flows from about 1.3, 1.5, I think up to 2 million years ago.
Okay. Yeah, classic. From Charles W. 53, any progress on being able to make tomographic images 3D below the surface of an area?
Yeah, there are, and those images exist. We put a few of them on. Well, they were featured in this series we have called Caldera Chronicles. 3D images of what the geyser systems look like. We also have kind of 3D-ish images of what the seismic velocities are like at deeper levels to look at what the magma chamber must be like. It's difficult to represent them, and so oftentimes what we do is we show these cross sections or perspective views. A few places you can sort of grab the thing and rotate it around and look at it in different ways, but usually we tend to try to visualize it in 2 dimensions, so that we can kind of map out the main structures. But yeah, that sort of 3D imaging is available, and we've been using it to not only map out the shallow geyser systems, but also the deeper magmatic system beneath Yellowstone.
Okay, Jeffrey Porter wants to know, the first boreholes in Yellowstone were conducted in 2930, the latest in 0708. Have you studied these samples? What can you tell us about them and the future of drilling in the park?
That's an excellent question. Yeah, some of the first drilling was done in the 20s, and then there was another phase of drilling in 67, 68. And then most recently, in 06, 07, 08, when there were boreholes installed that were instrumented. There were some borehole strain meters and tilt meters and seismometers that were put in those holes. And it has been incredibly valuable because you're actually getting that direct geologic view of what's happening. So boreholes have been outstanding for better seeing the geology. And I'll give you a great example of how that's used, going back to the Biscuit Basin explosion. So that area, Biscuit Basin, in the parking lot, that was one of the sites of drilling in 1967, 1968. And so we know from the drill log that right at Biscuit Basin, there's about 175 feet of glacial material. So back, over 14,000 years ago, Yellowstone was covered by an ice sheet that was a kilometer thick. And in places that were warm, Upper Geyser Basin, any of the geyser basins, lots of material sort of accumulated in those areas and kind of rained out when the glaciers finally went away. So you have these thick sediment piles that are sitting on top of a basement that's made of this rhyolite lava flows that were pre-glacial. The explosion at Biscuit Basin, when you look at the geology of the rocks that came out, it's all glacial debris, sandstone, siltstone. There's no rhyolite, that basement rock, anywhere in it. So that tells us that all of that material that exploded, the explosion itself was rooted in that shallow subsurface, no deeper than 175 feet or so deep. So yeah, the drill holes have been absolutely essential for being able to interpret some of what we see at the surface. There aren't any plans to do any more drilling at this point. As you might imagine, it's a pretty sensitive thing to do in a national park, especially one like Yellowstone. But who can say what the future might hold in terms of research drilling, either inside or outside the park.
Yeah, great data you get from those boreholes, but yeah, it comes at a cost from aesthetics and environmental point of view, and so they've got to balance all that. Okay, Oscar M, where is the oldest known caldera associated with the Yellowstone hotspot, and the age it's been dated at?
This is an interesting question. The oldest caldera that's known is probably McDermott caldera. It's about 16 and a half or so million years old, and that's the one that's sitting right in kind of northern Nevada, just south of the Oregon border, not too far from the Idaho border. That's the oldest caldera system known, but we think that the hotspot was around longer than that. So there is some geochemical evidence that there are Yellowstone-like lavas that erupted before that, but they're all smeared out into the coastal range in Oregon. And so we don't see them as nicely as we do since about 17, 16 million years ago, where the calderas just sort of march up the Snake River Plain.
And weren't those older ones basalts as well? They weren't rhyolitic calderas, they were a different chemistry, the ones they found?
Yeah. There were a lot of basalts in there, and it suggests that the hotspot was present offshore of Northern California, maybe crossed Northern California, Northern Nevada. There was a hiatus in volcanism. And that might have been because there was this downgoing slab of material in the northwest, and the hotspot couldn't punch through. And eventually, about 16 and a half or so million years ago, it did manage to punch through there. It hadn't erupted in 3, 4, 5 million years. And so there was a lot of heat and stuff stored ready to go. And when it punched through, it created the Columbia River basalts. So that was a flood basalt that sent lava from, Idaho, eastern Washington, eastern Oregon, all the way to the coast. So that's kind of the story that's out there for the history of Yellowstone volcanism and why it kind of got established really strongly 16, 17 million years ago and marched to its current location. I think it's still somewhat debated, but it's a pretty good story.
Yeah, there's some cool research going on there for sure. So stay tuned is probably the best way to think about it. So, okay, if you're good, we'll do maybe 10 more, this one more sheet. Is that okay?
Yeah, bring it on.
Okay, Mike's feeling fresh. All right, from Gabriel Ferreira. Although volcanic eruptions are difficult to predict, which volcanoes do you think could produce a VEI 6 or VEI 7 eruption in the short term, and do we have any protocol to deal with an event like that?
Well, there was an interesting paper that came out a few years ago by some folks that looked at kind of exactly that problem. The hype gets to be around these VEI 8 eruptions. These are eruptions that are humongous, like Yellowstone 631,000 years ago, or the Toba eruption 76,000 years ago, or the Taupo eruption 26,500 years ago. Really massive eruptions. They happen once or twice per 100,000 years. The VEI 7 eruptions, that's sort of one order of magnitude smaller, but still huge, happen maybe once every 1,000 years or so. So much more likely on the timescale of a single human life. And they mapped out a few dozen places around the world where there may be enough magma to feed such an eruption. And they're all over the world. In terms of kind of those big sorts of eruptions, one of the places that has been really dominant over the last few tens of thousands of years is Taupo in New Zealand, North Island, New Zealand. It's been the most productive area in terms of rhyolite volcanism. High silica compositions can be very explosive over the last 25,000 years or so. But there are a lot of places where that kind of thing can happen. That's one of the things that frustrates me about constantly hearing this sort of Yellowstone's a boogeyman and it's going to get us. There's a lot of volcanoes on Earth.
Right.
I don't understand why the focus is on Yellowstone when we know that it's, there's
we're
many other places that are.
We're all going to be watching Yellowstone while we get blindsided by some less well-known volcano in the Aleutians or who knows where, right?
Yeah, and those eruptions will be impactful. I mean, even a VEI 6, which is still quite a bit smaller than a 7, those are going to be impactful events that will have global climate implications, will be regionally devastating.
Yeah.
So those are the sorts of eruptions that are much more likely to occur on human timescales.
The most recent VEI 6 was Pinatubo was 6 in 91?
Yes.
And that affected
Pinatubo was like low 6.
Yeah, and that affected climate. I mean, there was global cooling from that eruption within a couple of years after, if I remember right. So. Yeah.
So these events are real big. The Tambora eruption back in 1815 was a huge one. That's probably the most recent really big one we've had, and it had a global impact on climate. It lasts a few years.
Yeah.
And then sort of goes away. But those things are out there. They've happened in the past. They're going to happen again in the future.
Yeah, the ones we should pay attention to. All right, from Susan Smart. Curious as to why the monthly discussion of deformation info for the park has shifted away from the two resurgent domes and Norris to other stations.
So the station that I usually show in the monthly update is the White Lake Station, and it's on the Sour Creek Resurgent Dome on the east side of the caldera. And that station has had a failure. So the receiver that was operating out there has failed. So it needs to be replaced. So instead, I switched to either the Hayden Valley or Lake sites. Those are both still on the Resurgent caldera, the Resurgent Dome, the Sour Creek Resurgent Dome. So they're just in a slightly different location, but they're seeing the same type of deformation. And the White Lake GPS station should be upgraded this summer. It requires a helicopter ride to get there, which is why it hasn't been done yet. So it's kind of hard to get to. But we have, there's a couple dozen GPS sites in the region and several on the Sour Creek Dome, several on the Mallard Lake Dome too. So that's why we've had that shift, is because the White Lake Station isn't working. But Hayden Valley is just across the river from White Lake, and then the Lake Station is just a little bit further south from there, and those show the same things.
Yeah.
And by the way, Susan, I just the other day put a copy of the annual report in the mail to you, so it should be on its way. Susan wrote me a while back.
Is this someone that works with you then?
No, she's interested in volcanoes.
Oh, okay.
So yeah, we just got our final copies of the annual report. So
awesome. She's on it. She's more knowledgeable than I am for sure. Okay, from Adele, why occasionally are earthquakes in Yellowstone removed from the USGS? Are those man-made quakes?
So actual earthquakes aren't ever removed, but sometimes the computer makes a mistake. And so I get these notifications as well, where it'll say earthquake magnitude 2.5, and then a few minutes later it'll say this event has been deleted. They're not necessarily man-made quakes, although that does happen. There are quarry blasts and so forth. Butte sees a lot of those.
Yeah, explosions or something.
Yeah, but occasionally there are environmental events that can be recorded by seismometers, and depending on noise levels and so forth, the computer can basically decide, I think this is an earthquake. And you can sort of look at the quality of the earthquake, and it'll be really poor quality, and it's sort of guessing at origin times. And when a seismologist actually looks at it, they'll see, this isn't an earthquake at all. It's some environmental noise or a combination of different environmental events that are making the computer think it's an earthquake. So this is why having actual seismologists review the data still remains critical. And what happens is, if there is a very small event that occurs and that the computer identifies overnight, sort of the next morning, a seismologist looks at everything and confirms whether or not it's real and assigns better magnitudes and better locations. And then if there is an earthquake of, I think, about 2.5 or greater, at least the computer thinks that it's 2.5 or greater, that alerts a seismologist immediately. So even if it's Saturday at 2 in the morning, the seismologist that's on duty gets a text message or a phone call from the computer saying, you got to look at this. And they'll go in and locate it, decide whether or not it's real. And if it's real, then they post that information. So it still goes through a human analyst, because even with all these
control. Yeah,
exactly. Even with all these advances in AI, computers still make mistakes because they don't yet have the experience that a human seismologist does in being able to tell a real signal from noise and things like that.
Just looking at the waveform or whatever it is with the specific seismic events.
But it's getting better. I mean, AI is changing the way some seismology works, and there are some tests going on with applying AI to Yellowstone seismic catalog. And can we do better than human seismologists in locating events? It's still not perfect by any means. The false alarm rate is relatively high, but a lot of these techniques involve learning. And so the more data we can feed one of these systems, the better it's going to do. So that's, I think, an area where worldwide we're seeing that sort of thing explored.
Interesting. Yeah, I didn't know that either. All right, from Dan Cooper, what's the total number of monitoring stations in the GYE? Deformation, audio, gas temperature monitoring, etc. I'm not sure what GYE stands for.
Greater Yellowstone Ecosystem.
Oh,
so that's the whole area around Yellowstone, not just the park itself. And let's see, it's a lot. I don't have that number off the top of my head, but for example, there are 46 seismic stations, or 47 now. We put one in last year. So 47 seismic stations in the greater region. And that includes stations that have multiple channels. So different frequencies they measure, horizontal,
Right.
vertical. And when you add up all the channels, you get well over like 120 some channels. There are over 30 GPS stations. We've got 10 river monitoring stations, and those monitor stream flow, river chemistry, things like that. We have a network of temperature sensors at Norris Geyser Basin. There's 9 of them there. We have 1 really good acoustic station. And that's where I'd like to see more work done. And it's in our monitoring plan for the next decade that we want to put out more of these acoustic stations because they are going to sense some of these explosions.
Yeah, I was going to say that's the smoking gun for the hydrothermal explosions.
Exactly.
Yeah.
Yeah. So the really good acoustic station we have is located at Norris Geyser Basin, and it was too far away to hear the Biscuit Basin explosion, but it heard that explosion on April 15th at Norris. So I think
it was
that's
way smaller, but just closer. Yeah.
Oh yeah, much smaller, but it was half a mile away. So I think deploying more of those types of sensors is going to be a focus of the monitoring in the future.
And do those
everything else is very well covered.
And do those relay data like in real time, or do you have to go and get the data, or it's continuous feed?
It's real time. So the acoustic data, the seismic data, the GPS data are feeding things in real time. So during earthquake swarms and things like that, we're sort of just watching the
everything
things
else
come in.
Oh, that's great. Okay, from Big Red Tower, what would happen if the heaviest part of the Rocky Mountains in Colorado had floated onto the Yellowstone hotspot?
Well, this experiment, sadly, we're not going to see the result of this experiment, but it's kind of happening. So the idea here, I think, is if you had really thick crust sitting on top of where the Yellowstone hotspot is, what would happen? Because for its history, last 17 million years or so, Yellowstone hotspot has been beneath relatively thin crust that's being pulled apart. It's stretching. That's the basin range.
Yeah.
So it's been able to punch through that. But if you put much thicker crust on the top of the hotspot, would the hotspot be able to punch through and feed volcanic eruptions? It's an open question, but it's going to happen. If you look at the trend of the hotspot across the Snake River Plain and out to into northwestern Wyoming, the next stop is northwest of where Yellowstone is now, and that's the Beartooth Plateau. That's an incredibly thick crust, area of thick crust. Will the Yellowstone hotspot be able to burn through that?
Yeah.
We don't know. There are some people that claim that the reason that the hotspot seems to be waning right now, it's not erupting quite as frequently, is because it's starting to encounter this thicker crust. But we don't know, and we're sadly not going to be around, at least that's on this. We're going to be around to see the results of that experiment. But it's a good question.
Yeah, I thought too there was something, I didn't catch the full presentation. I think it was geologists of Jackson Hole or something had done something on, someone had presented on the trend of the Tetons to the north, like they get kind of obliterated. So even though that's thicker crust, maybe not as much as the Beartooth Plateau, that the hotspot does have an effect on just kind of, obliterating. And that's what happened in Idaho too. I mean, we had these basin and range structures and mountain ranges that went across the whole area where those mountains, they're gone. Like the rocks are gone underneath the Snake River Plain. Like it just obliterates things. So in my mind, it might struggle a little bit more and take longer, but I don't think it's too much of a barrier for that volcanic activity to eventually punch through and cause changes.
Yeah, that's a funny thing to mention, that you see like the Teton range and the big faults that come with the Tetons come into the south part of Yellowstone and disappear. Yeah. And then out the north side, you get faults like the East Gallatin Reese Creek range.
Yeah.
And so these faults, probably go right through Yellowstone. And we think maybe some of the seismicity patterns we see are related to these north-south faults that you don't see anymore because a hole got blown in 631,000 years ago.
Right.
So yeah, the mountain ranges would have gone all through there and then got just blasted apart.
Yeah. So who knows? Okay, let's see. I lost track where it was. Let's see. Oscar M., if funding wasn't an issue, what improvements or programs would you like to see at Yellowstone? So there you go, pie in the sky. Mike gets to spend as much money as the government doesn't have or may have.
So there's a caveat to this, And that's that we do feel that we are stewards of the park and the landscape. So one thing we don't do is go willy-nilly, put stuff everywhere and not worry about the impact we're having, because
Right.
Yellowstone is an amazing place. It needs to remain an amazing place. So we do our best to not mar the landscape or do things that are going to cause damage to the environment. So if I had the ability to say we're going to put more sensors out and we're just going to do it, infrasound, the acoustic sensors would be very high on my list, because maybe these explosions that we've been talking about, we know they happen in the backcountry, but we don't know much about their frequency. And so if we could really map that out, and acoustics would probably be the way to go, that would give us a much better sense of, especially the small explosions, how often those are occurring.
Yeah.
At this point, we just sort of got to get lucky. Got to see one seismically or trip over one when you're out in the field working. That would be incredibly high on my list. I think there's also opportunities for geophysical sensors that maybe don't get enough attention. Things like magnetotelluric measurements. There have been a lot of measurements like that in Yellowstone, but not a lot of continuous monitoring of magnetic or electrical resistivity, things like that.
Right.
And that water moving around in the subsurface is pretty conductive. If there were changes in the water system at shallow levels, we might be able to see it with resistivity or magnetics. So that could be a growth area as well, especially for monitoring the hydrothermal system.
Yeah. Well, put it in your next budget proposal. Let's see. How expensive are those acoustic instruments? Are those?
I don't know. Everything, it feels like everything costs a few $1,000s, but then
Right.
there's the cost of all of the support equipment, solar panels, batteries, housing, and then there's the cost of getting there, which like that site out at White Lake with the GPS station, you got to fly there. So the costs of these things are much more than just the sensors themselves.
Yeah, installation. Yeah, just getting the data continually. Yeah. Okay, let's see. A couple more here. Shadow Catcher Fox. The continent has drifted a good distance over the last 630,000 years. Is Yellowstone really over the mantle plume's sweet spot anymore, or has that moved on?
Well, we don't see any evidence from tomography, so the seismic imaging, seismic velocities, that the hotspot is really, moved a lot to the northwest. So it does still seem to be connected. And probably what happens is an area remains connected for a while, even as the plate, moves over the hotspot, just because it's helpful for it to do that. Same thing happens in Hawaii, where a volcano will be active for quite a while as the plate moves over the hotspot, and then eventually it fades as the plate moves that volcano too far away. So in general, these systems seem to be active for a couple of million years or so before the hotspot it moves on due to plate motion. Yeah, we've been active in the Yellowstone region for a couple of million years. So I think it's a good question to ask. It's not happening on human timescales, but we don't see any evidence of a new system forming off to the northwest. Yeah. So
it does seem like it's hard to know where Yellowstone's at in its sort of performance. Is it like halftime? Is it like in the third quarter? Is it in the waning stages of it? Or is that a good way to kind of?
I think it's possible. It's the 2-minute warning for Yellowstone.
Yeah.
The next game is going to pop up to the northwest, but we don't see any evidence of that, at least in terms of the seismic velocity measurements.
Yeah, it's just such a slow system in terms of its evolution and progress. So, yeah, interesting. All right, Rebecca wants to know, since you left the HVO in 2017, was it hard to not be there during the Hawaii fissure eruptions?
Yeah, in 2018, there was a huge eruption from the Lower East Rift Zone, and it destroyed 700 homes. And it caused huge numbers of earthquakes at the summit as the caldera collapsed. Caldera dropped by 500 meters.
Yeah, the landscape's totally different. Have you been back since then to see it?
Several times.
Okay.
Yeah, I've been back several times, and I went back a couple of times in 2018 to help, because in the no observatory has enough staff to sustain a big response. So we kind of help by sending people from the mainland. We'll go up to Alaska if there's an eruption up there and they need a hand so that they can sleep and have lives. And so I went over a couple times for that. It was hard because there's a great sense of community over there and seeing so many people impacted, and then having the observatory shaken to pieces, very literally.
Yeah.
The Hawaiian Observatory building is gone.
Yeah.
It was
just
destroyed
last week.
Yeah, and they finished knocking the building down. There will be a new field station up in the park, and there'll be a main office for HVO, a new building that's being constructed down in Hilo. But the landscape is different, literally, and I think the landscape of the Hawaii Volcano Observatory is different. It's a new phase. It's not bad. It's different.
Just
possibly very exciting that it's a different start. But it was I saw what it was doing to my colleagues. I mean, it was traumatic because of the massive response that was required. I am glad I was able to help in my small part, but I don't envy my colleagues who lived through that, living on that island and having to sort of have
right when it's impacting your neighbors and your friends and family, like on that scale. Like it wasn't just a couple homes, like you said. It was, and I was there in 2018, that in early June, and people living in tents in the park in Puna, or in Pahoa, I mean. It was exciting geologically, because like, wow, this is something we haven't seen before, but the impact was just really sobering.
Yeah, and it lasted for 3 months.
Yeah.
Constant earthquakes, lava just sort of marching to the ocean and covering swaths of land. It was exhausting and traumatic for the people and for the staff that were trying to, track things and provide information to the extent that they could. So I felt very badly because I wasn't there to help out, but I tried my best to contribute.
Yeah.
That was a rough time for that island.
Yeah, definitely. So, yeah. Okay, back to Yellowstone. Jim Sadler wants to know, as the Yellowstone hotspot plume encounters thicker, colder Archean and Proterozoic crust as the North American plate continues moving, will the hotspot have more difficulty burning through the crust in the future? I think we kind of covered that a little bit.
Yeah. But I mean, I think it probably will, because if you buy the idea that, 20 million years ago, the hotspot was sort of being blocked by that downgoing slab, under northwest Nevada, so it wasn't erupting. That kind of suggests, if there's a thicker bunch of stuff that it has to get through, maybe it can't get through it as easily. Of course, that ended with a flood basalt, so
right.
Eventually, the hotspot would probably win. Yeah,
eventually. All right. Well, last question, Mike, and I appreciate the time you've been able to spend here. There's more questions than I think we have time for, but this one, our good friend Amanda Jo, who's one of our moderators, a different viewer asked this, but she really wants you to answer this. She's like, make sure he answers this one. So we'll have this one as our final one here. And if we didn't get your question, I apologize. We'll try to have Mike on another time and maybe do a follow-up. From That Random Beast, if Yellowstone is still getting new magma, is Yellowstone still getting new magma? And if so, why hasn't it erupted for such a long time? And that's a good fundamental question.
I love that question, and I wish I had a really good answer for that. It does seem that Yellowstone is getting new magma. Part of the reason for that is there's a carbon dioxide emissions. Now, that's coming from multiple places. There's a lot of limestone beneath Yellowstone. You heat that, it's going to release carbon dioxide, but that's also a sign of deep magma input. So we do think that it is getting some input, but it hasn't had an eruption of any kind in 70,000 years. And it's not like the whole area is buoyed up because of the great heat, but it's not inflating. In fact, over the last 10,000 years, we know that the volcano has actually subsided by about 100 feet. So this is an excellent question, and I wish I had a concrete answer. That's actually something I've been trying to understand myself, is what is the rate of supply to the Yellowstone system?
Yeah.
I don't think we really know. We can kind of make some rough guesses, but then you could say, well, all right, take that rough guess in supply, extrapolate it back 70,000 years, there would be a huge amount of magma that had come in since the last time Yellowstone erupted. It may be leaking out the sides. So maybe sort of leaking out towards the Snake River Plain or things like that. We don't have a good handle on that. That's a question right there that has interested me from the start since I started sort of really thinking hard about Yellowstone. I don't think we have a good answer.
Yeah,
I'm
and
sorry to say.
no, I think it's a good one to end on, and just kind of as a little addition. And we don't even know, do we know what kind of magma is down there? Because if it's consumed and assimilated a lot of this continental crust, then maybe it's transitioning mainly to its basalt that's underneath Yellowstone, or is there still a lot of rhyolite? And we talk about it mainly being crystallized, but we don't even know fundamentally what the composition of that whatever magma's down there, like what it is. Is that safe to say?
I think we think there's two systems, a basalt
Right.
system and then a rhyolite system, but we don't see any basalt in Yellowstone caldera. And that's probably because there's this low density rhyolite cap and it just can't get through.
Right.
And if we start seeing basalt eruptions in the caldera, that's probably a sign that Yellowstone's done.
Yeah, like we see in Island Park. Yeah.
Exactly. Island Park is covered in basalt. You look all through the Snake River Plain, it's all basalt. Beneath that is the rhyolite. So basalt is sort of the last gasp of these systems. So yeah, if we had a basaltic eruption in Yellowstone caldera, cinder cone or some lava, Hawaiian-like lava flow, I think we would all say, all right, well, this system is not as active as it used to be.
Yeah. So maybe that's a good indicator that it's not done yet. I mean, that it's not in that late stage part of its evolution, because we can see all the ones in the Snake River Plain that, they have the rhyolite and the explosive eruptions initially, but then they end up their late stage evolution is one of basaltic lava flows that fill in a lot of the caldera, and we haven't seen that yet. But maybe this will be one that doesn't, or who knows. So lots of unanswered questions. So
yeah, and our lifespans are so short compared to the lifespans of these systems. It's frustrating to not know how the story is going to end.
Right. Yeah. Well, this has been great, Mike. I appreciate you taking the time with us. I know the viewers have been just probably really excited to have you on here. Thanks for covering so many questions with us, and hopefully we can maybe circle back either just for some more follow-up questions, or if there's something else significant that goes on in the park, we can maybe circle back and talk with you. But thanks for being a great ambassador of science education and your role with the park and the USGS. Appreciate it.
My pleasure. I think if people would like more information, we do put out this weekly series of articles called Caldera Chronicles. And that's something that you can get on our USGS Volcanoes social media, or subscribe to get it via email, or just read it on the website. I can put a link in
the video description too for folks. Yeah, that'd be great.
Yeah, and then we put out annual reports every year, and then we do try to do monthly video updates as well. So, and I'm always happy to answer questions. So if people have questions, they can sure feel free to drop me a line.
Yeah. So, no shortage of information coming out of the YVO. You just gotta sign up and be willing to find it, or just be on the right kind of channels. But you guys do a great job, I think, of just providing information about what's going on with Yellowstone, because people are obviously very curious about that. So
easy to see why. It's a spectacular place.
Yeah.
Yeah, and let me get a shout out too to my cousins, Sage and Hawkeye, volcanologists in training.
Oh, where are they at?
They are upstairs right now in
okay.
Seattle. I'm in Seattle, visiting them, and I'm trying to get them into volcanoes.
Oh, excellent. Well, you're there like right now. You can make a big difference and run them through some drills and
we can see Rainier. It's a beautiful day.
Oh yeah, just so inspiring. So, well, great. And it'd be great to either do this again or maybe do something out in the field in Yellowstone. So thanks again for your time, and we'll go ahead and let you go. Appreciate it, Mike. Take care.
My pleasure. Take care, Shawn. Thanks for having me.
All right. See ya.
Bye-bye.
All right. Can you guys see me okay? Great. Yeah, let's just put something else up here as a background instead of this thing here. Awesome. Well, I hope that went well. I know we had some trouble, and we're probably still having the echo issue. I'll try to figure that out, and I apologize. But once I realized it was going to be good enough to get through and do the interview with him, I just didn't want to take more of his time with me futzing around with hundreds of people watching and trying to chime in with what I should do. So anyway, hopefully this was helpful. Mike was a tremendous guest. I want to again thank him for his time. Learned a lot about Yellowstone. There was a couple questions we weren't able to get to completely, so I do apologize for that. We'll try to get to those some other time. And hopefully this was helpful. Thanks as always to Amanda Joe and Susan Helmer for their great job monitoring the live chat. I'll go back through this later, and I will try to see if I can figure out a few fixes here on my end as we continue to do these interview series with the audio. I do apologize for that. I am not an audio engineer. I was running this, the Zoom was with Mike, and then I was running it through OBS Studio, and then obviously through YouTube as a live stream. But I think we've done this before, so I'm not sure what's different or if there's a setting I missed somewhere along the way. So hopefully it was helpful at any rate, and we'll continue with these. Look forward to our next one here in a few weeks. Not sure if it'll be a live stream. It might just be a video with Robin Hendrick at Zion National Park. But thanks as always to our moderators. Thanks to our great viewers and your great questions that you submitted. You guys are on top of things. I learned just as much from you as I probably put out there in terms of trying to educate as well. So thank you to our great geo-learning community. I'll put the link to the Caldera Chronicles on the video description and some other things there as well related to Yellowstone, so you can circle back to some of the USGS information they have about Yellowstone. But thank you all for your time and for your energy today. It was a really productive session, and we'll see you next time. Take care, team.